Okay, so let's dive in. Picture an animal from millions of years ago, an elephant relative, but it looks like it was put together completely wrong. We're talking about a creature that people say had the entire garden shed on its face.
That's a great way to put it. And we're talking about Platybelodon. Its name literally means flat-tusked animal.
And it looks almost, cartoonish. But the science behind it is incredibly serious.
It is. It's easy to just see it as this paleontological oddity because of that jaw, but what we've learned from it is, or it's profound, it's a textbook case of extreme specialization. And maybe more surprisingly, it's become this critical marker for dating our planet's history.
And that's really our mission for this deep dive. We're going to take what you think you know about elephants and just, well, set it aside. We're going to trace its evolutionary journey, figure out the mechanics of that jaw, and then see how its fossils help us date the rise of entire mountain ranges.
To give you a sense of scale here, Platybelodon is part of the order Proboscidea. That's the group that includes modern elephants. And this lineage, it includes the largest land mammals that have ever lived. I mean, think about its relative, Paleoloxodon pneumaticus.
Asian straight-tusked elephant.
Exactly. It stood over 5 meters at the shoulder. It probably weighed a staggering 22 tons. These were just colossal animals.
22 tons. Wow. Okay, so that puts Platybelodon in a slightly more modest category, I guess.
Right. It was still huge, don't get me wrong. It belonged to an extinct family called the Embelodontidae. They were a bit smaller than today's elephants, maybe 3 meters long, weighing 2 to 3 tons. And they lived during the Miocene, about 16 to 11 million years ago. But the size isn't the real story. The jaw is.
And what a jaw. I mean, it's this unbelievable piece of anatomy. It's not just big teeth.
No, they're modified second incisors that grew right out of the lower jaw, pointing up and forwards. It's what gives it that famous spoon-jawed or shovel-tusked look.
Shovel-tusked. That's the key, right? Because for a long time, that's what everyone thought it was for.
Precisely. The dominant theory for decades was based on where we found the fossils. They were almost always found near what used to be rivers or lakes. So the natural assumption was, well, it must be using these flat tusks like a shovel.
To scoop up soft plants from the water.
Yeah, scooping up vegetation, mud, roots, anything soft, probably with the help of its trunk. It just seemed to make perfect sense.
It looks like a scoop. But this is where the story takes a huge turn, one of those great aha moments in science. That whole shovel idea, it turned out to be completely misleading.
It really did. The turning point was when scientists started looking really, really closely at the wear patterns on the fossils themselves. If you're using your teeth to scoop up mud and gritty things, you'd expect a certain kind of damage, right? Sort of blunt, deep abrasion on the bottom and the tips.
Like using a metal spoon on gravel.
Yeah.
It would just get rounded and worn down all over.
Exactly, but that's not what they found. Instead, they found this very specific, very characteristic curved wear pattern, but only on the inner edge of those lower tusks.
The inner edge, so not from scooping.
Not at all. This was the result of consistent sideways friction. The evidence showed that the jaw was being used to slice vegetation. It functionally turned that anatomical shovel into a natural scythe.
A scythe. That changes everything. So it wasn't dredging up soft stuff from the mud. It was actively cutting something tougher.
That's the implication.
Yeah.
It suggests it was eating things like tough grasses or reeds that needed a sharp, precise cutting edge. It wasn't just pulling up its food, it was performing this mechanical pre-processing step before it even started chewing.
Which brings us to the trunk. Because those old drawings, the ones from the 1930s, they always show Platybelodon with this wide, flat, almost paddle-like trunk.
The flap trunk, yeah. That's been pretty much dismissed now. There's no real morphological evidence for it, and it just doesn't make sense if the jaw is a scythe. Well, think about the mechanics. If you have a massive cutting blade on your chin, you need something to feed material into that blade. The trunk was most likely a powerful, flexible proboscis, just like a modern elephant's. It would grasp a big bundle of grass and then drag it across those sharp lower tusks.
Oh, wow, so it's using its trunk like a hand, holding the vegetation taut while the jaw slices through it.
Exactly. An incredibly efficient, specialized cutting machine.
It's just amazing. And what's even more remarkable is that, unlike so many other extinct animals where we just have fragments, we have this incredibly clear picture of Platybelodon's entire life.
The fossil record for this animal is just fantastic. Some of the finds are like literal snapshots in time. There's one quarry in Mongolia that yielded almost 10 complete specimens.
10 in one spot.
Yeah. And most of them were young individuals. The theory is that they died together in a single event. Maybe they got trapped in a bog that dried out. It's a tragedy it preserved for millions of
And
years.
the level of detail is just unparalleled, right?
Absolutely. One adult female specimen gave us this incredible gift. Scientists found the tiny, nearly complete skeleton of an unborn fetus right between her pelvic bones.
A fossilized fetus. That has to be exceptionally rare.
It is. It lets us look directly at their development, the size at birth, the proportions, clues about the gestation period. It gives us this view of Platybelodon from the womb all the way to adulthood.
And all that anatomical insight then helps us understand their social lives, especially when we look at the differences between males and females, the sexual dimorphism.
Yes, and this is where the tusks give us another fascinating puzzle. In Platybelodon, it was only the males that had large upper tusks. The females had much smaller ones.
Okay, so usually when you see that in tusked animals, it means the big tusks are for fighting, right? Male-on-male combat for mates.
That would be the immediate assumption. But here's the crucial piece of evidence that flips that on its head. Researchers looked at those big male upper tusks, and they showed no signs of wear at all.
None. But if they were fighting,
They'd be battered, chipped, worn down. The fact that they're pristine suggests they were purely for display, for signaling, a social status symbol, not a weapon.
that is such a subtle but powerful distinction. The tusks for show are untouched, but the tusks for eating are constantly being used.
And that's the absolute key. The essential survival tool, that lower slicing jaw, the scythe, it was the same size in both males and females, and it showed the same heavy wear patterns in both. This confirms that the lower jaw was the primary feeding tool. It was so critical for survival that it couldn't be changed, regardless of sex.
Survival trumps social signaling. That's a beautiful evolutionary lesson. And when you look at its cousins, you see just how fast this kind of specialization can happen.
It's truly wild. If you look at Embelodon, its North American relative, both males and females used both their upper and lower tusks for feeding. No difference. Then you have a more recent discovery, Aphanobelodon zhao, which was a cousin that had no upper tusks at all.
So in the same family, you can have tusks being essential for everyone, or just for show, or just gone completely.
It shows how quickly evolution can repurpose or even eliminate a feature depending on what the local environment demands.
Okay, so now we're going to make a shift that I find just amazing. We're going from biology to global geography. This funny-looking animal actually helped us date one of the biggest geological events on Earth. How does an extinct elephant become a clock for plate tectonics?
It's a spectacular example of different scientific fields converging. Platybelodon's existence, or more accurately, where it didn't exist, gives us this high-resolution clue about the timing of the uplift of the Tibetan Plateau.
The roof of the world.
Mhm.
So we're using fossils to see when an ancient travel barrier went up. What did it look like before Platybelodon was around?
Right, so if you go back to the Oligocene, that's about 34 to 23 million years ago, we find fossils of giant rhinos and other huge mammals both north and south of where the plateau is today. The conclusion is pretty clear. The landmass was there, but it wasn't high enough to be a real barrier. Big animals could just walk across.
It had a migration corridor.
Exactly. But then that window closes. When we get to the Middle Miocene Platybelodon's time, 16 to 11 million years ago, its fossils are found only north of the Tibetan Plateau.
Only north, and none to the south.
Not a single one, which leads to this massive implication. By the time Platybelodon was alive, the plateau had risen to a critical elevation. It had become a barrier, probably too high, too cold, too difficult for a large animal like this to cross.
So just by mapping where this animal lived and where it didn't, we get a clear time frame for this huge geological event.
We do. It tells us that sometime between the age of the rhinos and the age of Platybelodon, that plateau became a continent-shaping force. This animal with a scythe on its chin becomes an accidental but very accurate geological marker.
That is just incredible, the intersection of biological history and tectonic history. Okay, let's recap the big takeaways for you. We learned that the flat-tusked Platybelodon wasn't a slow, mud-scooping creature at all. It was a highly specialized slicer, a scythe user based on those critical wear patterns.
We also saw how evolution sets its priorities. The male's upper tusks were just for show, no wear marks. But the essential survival-driven lower jaw was identical and heavily used by both males and females.
And finally, its geographic footprint, the fact it's only found north of the mountains, helped scientists date the massive uplift of the Tibetan Plateau. It confirmed the plateau had become a migration barrier between 16 and 11 million years ago. It just shows how reevaluating old fossils with new tech keeps paleontology so dynamic.
And it leaves you with this really interesting final thought about adaptation. The Proboscidea order is so diverse. It gave us 22-ton giants, tiny island dwarves like Stegodon, and then Platybelodon with this unique jaw. So here's the question to think about. If that cutting jaw was so absolutely essential that it couldn't change between the sexes, what kind of intense, consistent environmental pressure could have driven that? What made a precise slicing tool an absolute necessity for every single member of the species? It makes you wonder what small environmental details drive these grand anatomical solutions.